Alright, so welcome to your fourth to last lecture here. Your homework was due yesterday, which is why I'm guessing it's a little quiet in here today. But that's okay. Let's see here. In terms of deliverables and stuff that you guys have left, essentially it's just your course project. You know, for the project, there's a couple things that you guys owe me, and all the due dates, including, I think, down to the minute, like what time, is listed in the assignment, right? So that includes a written paper in the format that I provided you guys. That way it's somehow a little bit more fair when it comes to the number of pages, because I noticed that you guys have really creative ways of filling pages in some of the project proposals. That aside, let's see here. Then there's a presentation for the class, right? And so in the last lecture, which is a week from Thursday, I believe, each of you guys is asked to give a 5 to 8 minute talk on your project. If you want to go over it or have me take a look, I'm happy to during office hours, whatever. But essentially, you know, your goal is to tell us about the technical tool that you implemented, roughly some of the ideas mathematically, and the extension that you did, right? I will cut you off at 8 minutes and like bring my like vaudeville style cane. The problem that students never realize in a class like this with course presentations is for every 1 minute that you guys are off, that's like a half an hour additional of class that I have to be here. So we're going to try and be really rigid about keeping you guys on time. So part of that, hopefully in the spreadsheet now there's a line for you to put a link to your presentation. So we're not going to do the whole laptop rigmarole, but instead what I've done is ask each of you to give a link to a Google presentation thing. What is it called? Google Slides. Which I think is fine. I know it's not the most beautiful slides in the world, but it'll work. And that way, essentially, we'll just close one and then open the next one and leave them on the same computer. So if anybody has any really strong objections to that, you know, some special thing you need to show or whatever, then obviously we'll deal with that. But otherwise, I think that'll be some more efficient. Do you guys have any questions about your projects? I mean, really, if it's not like 86% of the way there by now, it should be. So if not, you should email me and we'll find some time to meet and really get you to the point that it should be at. Yeah, is there anything I can clarify about how your presentation should go, what should be in your write-up, any other deliverables? Cool. You know, this class does have late days, so they do apply to your last homework. What I noticed the last time I taught at MIT is that some people just didn't do the last assignment or something because they somehow like didn't make the deadline. Like you can still do it and use your late days, and there's plenty of buffer before the end of the semester. If you have exhausted all of your late days, your options are, I'm going down the list of things I'm getting emails about over and over again. Your options are just do it anyway and get partial credit. There's a policy that's very clear in the course handout about how to do that. Or if you're experiencing unexpected or extremely high level of stress, then I actually encourage you to go to this S-cubed office at MIT. It's totally healthy. Students do this every semester, and you should go get help. If you don't, I will not be able to give you additional things in your homework. That's going to be our agreement, because otherwise this is not fair.
I think for grad students there's another office. I don't think it's S-cubed. I think S-cubed is undergrad, but there's something equivalent.
There's some equivalent, and essentially, I mean, you're not supposed to know this, but essentially it's really just a rubber stamp, right? If you go talk to them, they will email me and tell me to give you late days. But at least at that point somebody knows that you're stressed out, which is what I'm most concerned about. Your homework is kind of secondary. Good. All right. Well, if there are no other questions, then we're going to get started with today's topic, which is one that's very close to my heart because it's an area that I've done a lot of research in, and that's on surface correspondence. And so the image here, conveniently, is copy-pasted from one of my papers, is essentially some idea of what the input and the output is, right? That essentially your input is 2 or more geometric domains. And when I say geometric domains, I really mean it in that level of generality. So here we have like a triangle mesh, another triangle mesh that's kind of abstractly related, a point cloud, a toilet sign, a hand drawing, and in each case, our goal is to find the shared structure from one into the other. Yeah? And in particular, the object that we're after is either a mapping or a correspondence, right? Some list of pairs of points that tell me like the yellow guy on the first one is related to the yellow point on the second, is related to the yellow point on the third, and so on. Yeah? So another way of putting it is that essentially our question is which points on one object correspond to which points on another. And of course, as I pose it to you here, this is a super vague question, right? In particular, the word correspond here is really complex. And while there are a lot of geometrically reasonable ways to do it, similar to when we were talking about clustering problems, there's no like God-given platonic ideal for correspondence from one surface to another, right? And the example that you should keep in the back of your mind, actually there's sort of two good examples. One is, let's say that I give you a 3D model of a horse and a 3D model of a giraffe. Somehow we all expect that you could find a mapping from one into the other, and that there are certain ones that are more reasonable than others, right? If I took the head of the horse and mapped it to the tail of the giraffe, then obviously I did something wrong. But they're not the same animal, right? And any bijective map from one into the other is sort of subjective in the sense that like there really isn't any saying what point is sort of best matching to some other one, and you can come up with all kinds of different criteria, right? So similar to like, you know, I told you if you see a paper that says this is a paper on segmentation and this is the segmentation algorithm you should use, you should be very suspicious because segmentation is not the kind of problem that like you just segment an object and you're done and you hand it off to your end user. This is another kind of similar setup, right, where correspondence is a step inside of another pipeline, whether it's transferring texture from one 3D model to another, or like modeling or labeling the interesting folds on a human brain, are very different correspondence problems, and the objective functions and so on should be different for these. Yeah? Okay. So remember that we spent the last 2 lectures on registration, right? And the idea there was that I give you, for example, 2 scans of the Stanford Bunny from 2 different camera angles, and your job is to figure out a coordinate frame where they're in common. Right? Or similarly, we talked about non-rigid registration, which would be like, you know, I put Matt in front of a Connect, and he's, you know, doing the Macarena, and his arms are bending, and so on. So I don't expect to be able to rigidly align the frames anymore, but I do expect there to be some non-rigid deformation of one frame into the next that sort of, you know, gives me a reasonable notion of correspondence. So when I give you questions like mapping between 2 brains or mapping from a horse to a giraffe, really the question that you should ask is, well, why is this any different from what we've already talked about? Yeah? And so can any of you guys give me some ideas of like what goes wrong if I like take ICP algorithms and plug it in, given a horse and a giraffe? And I'll speak at once.
You mean rigid transformation?
Yeah, like rigid or near rigid transformation. Like why?
It just doesn't make sense. Like you're not mapping the same structure on one animal to the other.
Exactly. So the operative word here is structure, right? As Danielle suggests here, right? Essentially, what we're asking is to somehow map from one object into another while preserving structure. And the structure that we came up with in the last few lectures were things like stretching and bending, right? But at some extreme, it's not so clear that that's the right thing to do, right? That maybe you have individual segments that you want to be preserved, right? That would make sense for the horse and the giraffe when your neck gets longer. Or maybe there's semantic information. And regardless, remember there's another drawback which is a little more concrete, which is the ICP algorithm and friends, right? Things like non-rigid ICP depend really, really strongly on having already a pretty good initial guess, right? But if I give you like, you know, a horse, a donkey, a giraffe, and whatever, a zebra, and I ask you to put them all in the same coordinate frame, and that's going to be what I use to initialize this procedure where I grab closest points and then maybe I deform a little bit and I iterate, how well do you think we're going to do? Not very, right? And things get even worse in the presence of weird topological features, right? Like maybe I clasp my hands together and all of a sudden I'm a torus, or you know, all kinds of things can fall apart. And in each case, the basic algorithms that we talked about before, which are really effective for like tracking someone in front of the camera, are not so effective for these more abstract tasks. Cool? So that's our cheerleading session. That's what we're after for today. Right? In other words, we're really seeking shared structure instead of just alignment. Right? And so the example to keep in your back of your head is you have all kinds of different 4-legged animals. In fact, the typical data set that people use to test a lot of these correspondence algorithms, at least in computer graphics, is literally a data set of 4-legged animals. And somebody has painstakingly marked points that we're pretty sure should correspond, and then you measure deviation from that. This is really tricky, right? I mean, when we start using words like structure and semantics, all of a sudden it's not so clear mathematically exactly the best way to model it. But what we'll try and derive today are some reasonable models that measure things like stretch and matching of features and so on. And then what you should keep in the back of your head, and actually what's an open research problem, is how to couple these nice geometric ideas with some notion of machine learning. right? And this is actually quite a tricky problem, right? Because at the end of the day, you really do want something that's like bijective and you know, distortion-free and so on. But you also would like to take, you know, the head to the head and the tail to the tail, and somewhere halfway between that is what we're really after. Okay. So there are all kinds of different applications of correspondence. I don't think it's too hard to justify why we need this kind of machinery to geometry pipeline. Some ones that have been proposed in the past, some kind of goofy ones in the computer graphics literature include like moving texture from one shape to another. So here we have a very poorly textured horse, which is transferred to a very poorly textured camel. Obviously, 13 years later, we can probably do better in the individual frames here, but certainly the overall goal is quite similar. Or maybe you can take segmentations of individual objects and transfer them from one to the other. In particular, segmentation transfer is actually kind of an interesting question. Remember, we talked about surface segmentation in kind of a vacuum, like given one surface, come up with individual pieces that parcellate that surface into reasonable parts. But of course, oftentimes what you really want is some notion of consistent segmentation, like the same segments appear on the horse and the giraffe and whatever. And so then in that case, it might actually make sense to come up with some rough mapping from one object to another and then just transfer labels that way, rather than just segmenting every object starting from scratch. And in fact, in our next lecture, or set of slides, depending on how slowly I talk today, we'll talk about consistent surface mapping, which deals with more than two surfaces at a time. And in that case, really, segmentation transfer makes a lot of sense. Right? You have a whole data set, you can all have a consistent set of labels. One of the kind of fun things you can do is play a little bit with different types of domains. So for instance, here I would argue that the topology of this graph on the left-hand side has something to do with an alligator, right? And in this very abstract task, you might try and ask, well, what exactly? Right? And of course here, ideas like ICP just make no sense at all, right? I mean, it's like you're kind of hosed from the start, because there's no notion of alignment to be had. Right, but even so, both of these objects are pieces of geometry, just in very different sense, right? I mean, on the right-hand side, we have the alligator, which is equipped with geodesic distance function, right? So we can think of the alligator like a metric space, like we talked about before. And on the left-hand side, we have a graph. But graphs, as we all know in computer science, also have a notion of distance, right? They have the shortest path distance. And you might ask, can I find the mapping from this graph on the left-hand side, this completely abstract object, onto the alligator that makes sense? Yeah. And I would argue that, in fact, there are at least some maps that make more sense than others. Whether there's a globally optimal one, that's a little bit of a different question. Yeah. And in fact, you can see in this particular piece of research, there have been people that followed up on exactly this experiment. I noticed there's one coming out at SIGGRAPH this year. We made an engineering trade-off, which says, like, for example, the orange hand of the giraffe model on the left-hand side. Well, this graph is not enough to disambiguate left from right. Right? I mean, a graph is just an object with a distance function. And so instead, we just chose to light up both hands. Right? Which you can imagine in some applications that's useful. In other applications, maybe you just want some bijection, you don't care if it's the one that takes left to left or right to right. And then in even more applications, maybe you need some notion of handedness. Right? Each one of these is slightly different context. So we're starting our lecture today to kind of give you guys a feel for why, when I say correspondence, like it's very easy to kind of say, oh, correspondence is given two surfaces finding a low deformation map from one to the other, but that's not the whole story, right? And there's really a lot of different variations of these problems, and each one is equally difficult and completely different from every other one. You know, this is a great source of just like tons and tons of really tough technical challenges. There are other kind of fun applications that are completely outside of graphics. So, for instance, in paleontology, right? Maybe I go to my favorite dig site, and what I recover is a big pile of teeth. Apparently this is a common situation for paleontologists because things like teeth and bones last a heck of a lot longer than organic material. Are teeth considered organic material? I mean, they are. Anyway, one way or the other, I end up with a bunch of teeth, and my question is sort of how did the teeth evolve from one another under the assumption that, well, you know, two creatures that are somehow close in evolution should have closely related teeth. Now, this is an assumption, right? It could be that some genetic event all of a sudden causes you to grow fangs. I will refer you to the biology department to clarify matters in that respect. But certainly, mapping between teeth that from the same species maybe makes sense for understanding things like eating habits and patterns, right? That maybe you wear down on your teeth a particular way. Right? In fact, just recently I learned that apparently the people that do, what is it, the Invisalign, you know, the Invisalign braces really do use 3D scanning, right? What they do is you bite into this impression mold, and then they mail it into this company that takes a 3D scan of the mold, and then it computes the geodesic between your current set of teeth and the ideal set of teeth that are achievable using what's in your mouth. And then what they do is they 3D print a series of mouths that are closer and closer to what the ideal, and depending on how finely you sample that space, I think has some proportionality to the pain that you experience when you do ortho. Anyway, in all these different applications, there's slightly different contexts and reasons for computing a map. You can imagine a lot of different desirable properties for given objects, right? This is certainly one of many instances where we have something like multi-objective optimization, where you can't make all of these things happy at once. And different things you might want are that maybe you just want your mapping software to be fast and any reasonable component, right? At least one that doesn't map your, the face of the horse to the tuchus of the giraffe is okay. Or maybe you want something that's bijective or low distortion or just fully automatic or semi-supervised or whatever. In an ideal world, what you want is one framework that can cover all of this. And it might be that exists. We don't have it yet. But we do have a lot of variations of this stuff that are useful. So in today's lecture, essentially, or from a high level, what we're going to do is draw a lot of pictures of different correspondence techniques. As lectures go in this class, there will be a higher photos to mathematics ratio than some other ones. Because I think, given some of the skills that you guys have already developed in 6-8-3-8, it's actually pretty easy to kind of predict the technical tools that are sitting underneath the basic method once you see the outline. Right? Really, this is the same hammers we've already covered, things like exterior calculus and the Laplacian operator and embedding, and all these things all come up in nice application. Yep. So historically, sort of the first way that people thought of finding correspondence is in a way a totally reasonable engineering solution. And it makes really cute diagrams, like these kind of, they look like what do they call the water bears? These little organisms. But anyway, essentially, what you can do is take a 3D surface and parcellate it, run your favorite segmentation algorithm so that now it's covered in a bunch of little disc-like patches, right? And then you can take each pair of patches, which maybe is somehow easier to map than the full surface densely, right? Like I could extract a graph on these two objects, which at some level, it's pretty clear that the rhinoceros and the triceratops here have kind of similar structure, right? They have both a tail and 4 legs. I'll extract that graph first, use that graph to divide my surface into a bunch of little, planar disc-shaped patches, and then co-parameterize. Remember we talked about parameterization, which is taking a 3D surface and mapping it into the plane? So what I'll do is I'll take each of these little patches and map it into the same plane in 2D, and then just read my map as a composition of these two objects, right? So what machinery is needed here? Well, there's sort of two pieces, right? One of which is extract a graph along the surface. I believe these people did it essentially manually, which is like not a totally unreasonable task to ask your user to do, right? I mean, essentially you're asking them to click about 10 key points and then just use short paths between them. And then the other thing you have to do is parameterize. And if you remember all the way back to lecture 2 of this class, and it's kind of ancient history, we talked about a particular algorithm for mesh embedding. Right? And essentially what that algorithm did is it solved a linear system of equations that asked that every vertex in your embedding that isn't on the boundary end up at the average of its neighbors. Right? Does anybody remember what this is called, incidentally? The mapping from the 3D surface to the plane has a particular name in differential geometry. That's a long time ago. Now, this is called a harmonic mapping of your surface, right? And what operator do you think is hiding underneath this thing because I call it a harmonic mapping? The Laplacian operator, right? You can't get away from this guy, right? And so this is yet another case where essentially what we're going to do is solve Laplace of f equals g, and then what comes out is a nice mapping of your surface. So in particular, if you recall from a very long time ago, essentially the linear system that we're going to solve is that you can think of each of these patches that I want to embed as a graph, right? It has a bunch of vertices and edges. What I'd like is somehow that every edge in my embedding doesn't get warped to something super long in the plane. right? So my variables in my optimization problem are the positions of all the vertices here. Yeah? And my objective function says that I want each of the edges in the embedded 3D mesh to kind of have short length. Now, what is the shortest length I could have for every possible edge, right, if I didn't have any constraints? Well, it would be 0, right? I mean, and in a sense, that's the smoothest possible map I could have from a surface into the plane, right? I mean, if you differentiate it, you go, it doesn't change at all. It's super smooth. And so to prevent that, in this particular embedding technique, what you do is you extract the boundary of your region, and you just pin it. You just add a constraint that, for example, evenly spaces it around a circle, and you say, I'm not going to move those points, and I'm just going to solve the system on the inside. And this is called the tut embedding of your system, or if you add some weights, maybe it's harmonic, because you notice that if you take the KKT conditions of this optimization problem we've written down here, which we're not going to do in class, because at that point it would be like flogging on a dead horse, what you'll get is a Laplacian operator, right? So you might look at that and say, okay, well then I'll change the weights of Laplacian to use Laplacian in the 3D surface, and that's a totally reasonable thing to do. In fact, you can get a conformal map this way, which is kind of nice. Okay, so at the end of the day, what you get, right, by solving the system, remember the system essentially says we're going to place, the boundary points, and then we're going to ask that any interior point is essentially as the average of its neighbors, right? And it's the linear condition, right? It says if I sum up my neighbors and divide by n, I get that. That's linear in the unknowns. So there's a really nice theorem here, which is the Tut embedding theorem. Incidentally, I looked him up because I feel like people always say Tute in computer graphics. That's actually not true. He's British. He was involved in the British cryptography effort back in World War II. It's kind of an interesting guy. I encourage you to look him up. Anyway, what this theorem says is that as long as these fixed points you have on the boundary are mapped to a convex polygon, then the map that you get when you solve this linear system of equations is necessarily bijective. Right? In other words, no two triangles share a piece of the plane. Yeah, and this is a really nice property to have for these correspondence algorithms, right? Because essentially what it says is that as long as I put these boundary kind of triangles of the 3D object into correspondence with each other, then the mapping that I'll get from one guy into the next is a bijective map. Right? They won't share the same piece of the texture plane. Right? And it's pretty easy to kind of convince yourself that this is true. I don't think it's worth proving in class, but essentially, I mean, think about the linear condition that shows up in the system. Right? It says that you're sitting at the average of your neighbors. It would be very difficult to get a triangle that flips upside down and have that vertex of the triangle be the average of its neighbors. Okay? Essentially, this is just some formalization of that fact. Yeah? So anyway, what these mapping techniques do is really simple. You kind of find a common refinement of a very simple graph that sits on top of your two surfaces. You co-map each patch to the plane using, for example, this Tut embedding here. And then you just extract your map by reading the composition. Yeah? So the pros here are that, I mean, for one thing, this is very easy. It's very easy to compute this parameterization. And the applications here are quite straightforward, right? Because you really do get something bijective and smooth away from these curves. But that should be fishy, right? Because what's going to happen is that essentially all the distortion of your map is going to concentrate on these red lines here. And so, for example, if you use this, I paint a texture on the giraffe and then I map it forward to a horse using this technique, what you're going to see is on that texture, little shear points, right, where you marked this red graph, which is no good. We don't like that. So the cons here is that somebody have to mark these manual landmarks, and you, at the end of the day, you don't minimize distortion, right? You don't get a smooth map necessarily because of these singular lines here. And even away from the singular lines, a theme that'll come back here that's a little subtle is that it kind of looks like, well, okay, so yeah, on the red lines we're going to get a bad map, but maybe in between them it's good and it's kind of smooth looking because we solved this nice harmonic system. But notice that that system actually doesn't minimize the distortion of my map. What it minimizes is the distortion of the surface mapped into the plane. Right? So you take two surfaces and you map them into the plane, and those two maps are low distortion, but it says nothing about the composition of the two. This is actually a theme in differential geometry, right? You have to be quite careful. For example, if you want a harmonic map from one manifold into another, you might say, well, maybe I'll harmonically map them both into some plane where I know how to do it and then compose the two, but that composition doesn't necessarily minimize anything. It's a really tricky, subtle point, and a mistake that we make a lot in geometry classes. So this idea, up until a couple years ago, was considered kind of an old school idea, right? Like this, somehow it looks very manual. It looks very 90s, right? Like you're marking a lot of points here. Parameterizing, you can't prove a whole lot about it, right? This is kind of pre-geometry processing. But actually, the idea recently has come back into play in a really insightful piece of research. And I encourage you guys to read this paper, which essentially says, okay, this Tutt embedding theorem is only relevant to disk-like patches, right? But when I say disk, I mean disk topology, right? That you don't have any holes, it's not a sphere, it's just one, it's kind of, you can map it smoothly into just like a rectangle, yeah? Or a circle, I suppose. So what was noticed in this piece of research is that if I'm willing to make some identifications, I can construct interesting topological objects out of just planar pieces, right? And this story might be familiar to you. Right? So the typical example, which I'm likely to get wrong on the board, but I'll try, is let's say that I want a torus. Right? That's a donut. The only reason that I always use this example is because I can never draw any other shape. But that aside, so let's say that I want a torus, and I'd like to map it into the plane. Right? Maybe in particular I want to map it into a rectangle. Right? And for a long time when I was an undergrad in geometry classes, people always talk about flat toruses. And I took a lot of geometry classes before I took topology, and I was kind of like, well, that doesn't make any sense. Like, you can't have a flat torus. But in fact, you can, from a Riemannian perspective, right? And the idea here is let's say that I take a sheet of paper, in fact, another of our high-quality live demos. If I take a sheet of paper, which I actually did a pretty good job of approximating on the board here, and I wrap it up, I can make this into a cylinder. Yeah? And so the typical diagram people draw in topology looks like this. It says that what I'm going to do is take these two edges and glue them to each other. Right? So all of a sudden I should think of this rectangle not like a rectangle, but like a cylinder. You might not be able to see it, but that's what it is. Right? Because if I keep going this way, then I'm going to identify that top point with this bottom one and keep moving. Yeah? And similarly, if I wanted to take this is going to be harder than the sheet of paper. If I want to take this and make it into a torus, I could do one of those. Yeah? And roughly, that's going to take, oh gosh, I always get this one. This point to this point, so it looks like that. Did I do that right? I always get this backward. Yeah, and if I flip one of these two guys, then I get the Klein bottle, right? Right, so when people say flat torus, what they mean is a rectangle plus very particular boundary conditions that say, in fact, this point and this point are the same. Yeah? So the really interesting, fascinating, smart, cool idea in this paper, which I decided not to cover in a ton of detail in this class because we're kind of running low on time, but essentially this is the insight and then the details I'll let you fill in, are essentially you can take this Tutt embedding theorem, which is kind of easy to convince yourself of for just like polygon shapes, and you can actually expand it to include orbifolds. So in other words, to include tilings of the plane that you get by making these kinds of boundary identifications. Right? So what this allows you to do is to map bijectively surfaces that aren't just disk-like in topology. It's a really smart idea. So for example, if I wanted to take this line guy, what I would do is cut it, and the way to read this diagram is anytime you see two things of the same color separated by a vertex, they kind of get mapped to each other. Right? So for instance, if you see this red vertex and these two lines here, notice that you have red to purple on the left hand and red to purple on the right hand. This is kind of like folding it upward. Yeah? This is like giving you an origami, set of origami instructions for making the surface out of these little pieces. Right? By kind of gluing edges together. I suppose actually by gluing you're no longer doing origami. So that is, and essentially what this corresponds to is solving this Tutt problem on a tiling of the plane, where you just take this little rectangle piece, and you notice that, I can think about this like extending all the way into the plane, and notice, essentially when I think about this point, after having made that identification, this is like having a copy of this point here, 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 and so on, right? And so by applying this theorem in just the right way, they're able to extend it to all kinds of interesting topological objects and get smoothness. Now, remember I mentioned that algorithms like this are not designed to, notice that we only show mapping into the plane, right? So for instance, if I wanted to map from this jug into David here, right, I can map them both into the plane and then just, compose, yeah? But then, once again, there's no notion of distortion here. The distortion is the distortion of the map into the plane. It's not the distortion of the map from one surface into another. I can't emphasize that enough. Because that's actually the open problem here. is like if I have two surfaces and I want to minimize distortion, we actually don't know how to do that in this framework. You have to be quite careful. So for instance, this harmonic energy that wants to minimize edge lengths, it's very easy to give pairs of surfaces for which, if you try and minimize it, the solution doesn't exist, which is actually surprising. This is a differential geometry fact. That in order to minimize that harmonic energy, the target of your map has to be hyperbolic, or at most flat. So like mapping to the plane is okay because it's flat, but mapping from this jug into David here, if you try and minimize the harmonic energy, which makes the eigenvalues want to go to 0 once everything can collapse, you can actually have singularities, right? This is the same reason why mean curvature flow could fail. Right, so anyway, that's it. So, if I have, right, so one way to think about this mapping, which we'll talk about in a second, is if I have mapping from one triangle into another, and I look at the Jacobian, then what I want is that the singular values of this thing are all 0, right? That's essentially what this energy wants. It wants all the triangles to collapse to a point. What I'm saying is any energy that I construct out of this kind of a term, if I say, okay, I'm given two positively curved surfaces and I do gradient descent on this energy, I can actually develop a singularity. I can have things collapse to a point. This is the thing to search here is the Eales and Sampson theorem. This is a theorem in differential geometry that says the existence of harmonic mass. And you'll see that a condition there is that the target has to have non-positive curvature. And otherwise, the gradient descent procedure will fall apart. And for good reason. It's essentially, yet another way to think about it is like, geodesics are examples of harmonic maps from a line into a manifold. But if I compute geodesics on a sphere, they're highly non-unique, right? Like if I have two antipodal points, it somehow like gets in the way of these descent procedures. That's not to say that there doesn't exist a minimizer necessarily, but that is very difficult to find. Yeah. And in fact, if you do the wrong gradient descent procedure, you'll get these singularities, which apparently have something to do with black holes, but I'm not the right guy to ask about. Okay. They call it bubbling in differential geometry. Cool. So let's say that anyway. So we're going to step back. That was a pointer into some modern research, but let's step back into some classical stuff. Right, so let's say that we have this method and we have two drawbacks, one of which is that it's high distortion, but we don't know what to do about that. The other of which is that it's kind of manual, and we can get rid of that constraint pretty easily, right? In particular, we spent quite some time in this class talking about things like computing descriptors, right? And so a very reasonable pipeline here might be to compute your favorite like heat kernel descriptor or whatever, compute a few key points, and then maybe what I do is just try every possible mapping of those key points onto each other, run this algorithm, and then just choose the one that has the lowest distortion measure. And as long as you have relatively few key points, that's okay. Right? And so there are all kinds of different people that have proposed essentially this technique. So that's one in this 2004 paper. So if you're going to do kind of a meta procedure like this, right, like choose a few key points and then call somebody else's algorithm, then you've got to decide what your criterion is for like whether you're doing well or not. And there are a lot of different ones to choose from, right? In particular, you could talk about conformality. Does anybody remember what that means? It's very Bueller here. What is a conformal map?
Angle preserving?
Yes, angle preserving. Thanks, Matthew. You can talk about area preserving map, which also has a fancy name that I've forgotten. It's not auxetic. It's that doesn't matter. Or you could try and come up with like some notion of stretch, like a rubber sheet, and try and preserve that. Right? These are all slightly different measures. Yeah? So, in particular, if we abstract a little bit, this goes back to the question a little bit. One way to think about how well your map has done, right, is to remember that if I'm mapping from one triangulated surface into another, then essentially what this gives me is an image for every triangle in 3D that's somehow distorted from where it started. Right? And if that image, for example, is a rigid motion of where it started, then maybe I'm happy. And the question is, well, if it's not a rigid motion, then what is it? You know? So essentially, a lot of literature has been devoted to how to measure how distorted a single triangle is. And then essentially, what you do to build up a distortion measure for your whole surface is just sum over all the triangles. Right? And so in other words, there's a distortion energy that's equal to kind of the integral, right? That's the sum of area times distortion per triangle. Does that make sense? So, okay, so then my question is, kind of obvious question from here. How would you measure distortion of a single triangle? Like, do you guys have any ideas? How can I go about this? Well, we have one tool that we introduced a couple weeks ago when we first started talking about the Lopatkin operator, which is the finite element method. Remember that the finite element method essentially puts some assumption on what happens in the inside of a triangle relative to what happens at the vertices. And this is a really nice way to think about what's going to go on here. Yeah? In particular, hopefully you guys all agree with me that if I take two triangles in 3D, I can rigidly put them in the plane. Yeah? If you haven't, then we should talk after class. But okay, so it's enough for me to give a distortion measure for two planar triangles, right? And then just kind of compose, assuming that it's rigid invariant with a rigid method in the plane. Cool? Alright, so let's say that I have, here's one triangle, and now I have to label the vertices, right? So we'll say this is A, B, and that other letter, and then we have another triangle here, which is somehow, you know, a mapping of this guy, so maybe this is A prime, B prime, and C prime. And essentially what I'm after is sort of like if I take C to C prime, B to B prime, and A to A prime, then how distorted is this triangle? Yeah? So in other words, like I'm thinking there being some map, phi maybe, from one into the other, that measures how stretchy it is. Yeah? So, right, so if we're going to do the finite elements method, and this is not the only way to do it, but it's one reasonable one, then essentially what I have to decide is like, if I mark this point here, well, I have to figure out where it went, right? And it's actually not super clear if I just give you 3 marked points. I mean, you can imagine that like somebody who's evil like stretched out just the inside of the triangle. But somehow that would be reading more information to the data that we have. Yeah? So, in the absence of more information about our map, what assumption might we put on it? I mean, just in general, when I have a function like, well, it's certainly not a constant, right? My triangle is stretched out. Mazzy?
Half line?
Yeah, half one. He has a leg up, if you guys are wondering, because his course project involves this kind of stuff. Right, so you know, a linear map doesn't quite work because linear maps take the origin to the origin. There's no notion of origin here, right? So then the next best thing to a linear map, as Mazzy tells us, is an affine map. So in other words, I can think of the map phi of S, at least restricted to the interior of a triangle, right? As some linear thing. Yeah? And so the first question is, do the degrees of freedom work out? Yeah? And the answer is actually yes. So remember, we're in the plane here, so J is going to be 2 by 2. Yeah? And C is going to be 2 by 1, so there's 6 unknowns. Yeah? And notice how many conditions do we have? We have 3 points, and each one of those guys has an x and a y coordinate. So there's 6 unknowns and 6 knowns. So you can solve the system of equations for J and C. And then my question for you is, should this energy depend on C? Typically, I mean, unless I have a really good reason. What is C? C is just like a translation of the triangle, right? So probably not. Yeah? And similarly, like if I take J and maybe I just rotate this triangle, and maybe I rotate my coordinates too, just for fun. I can do whatever I want. Yeah? Do I expect this thing to be affected, the distortion to be affected here? No. So, can anybody kind of guess, other than Mazzy, what sort of, if I'm looking, so for one thing, I can ignore C, and I'll let you guys work out at home how to compute C and J, otherwise I'll be doing this project for you. But that aside, so we've decided our mapping doesn't really depend on C. One way to do that is just to subtract out A and put it at the origin. But what property of J should it depend on? Like, we only have so many hammers in the algebra. Jared, what could we use?
Like the shear?
Yeah, the shear. So how can I measure shear? Or how can I measure shear and stretch and so on? Yes?
Condition number?
The condition number. That's one notion of stretch. It's kind of a weird one, actually, because you're dividing by a single value, right? But in general, I mean, for one thing, it depends on exactly what you're after, right? If you want a conformal map, that's different from low distortion, like as rigid as possible map or something else. But what I would argue is that really what your distortion measure should depend on is what we call the singular value decomposition, which is something we know very well. Yeah? So in particular, remember we already used this in class a couple weeks ago. I can take J and I can decompose them as U times sigma times V transpose. And in this particular case, since J is square, right, we know that this is equal to U, and then you can think of this like sigma 1, sigma 2, V transpose. My question is, should this depend on U and V? No, right? Because remember, U and V are orthogonal matrices. They're like rotations, right? So at the end of the day, if I want to measure the distortion of a single triangle, essentially what I can do is enter, and I want it to be rotationally invariant, then I can encapsulate it all into a function that is, only depends on sigma 1 and sigma 2. Somehow we reduced our problem quite a bit. Yeah? So for example, in the Dirichlet energy, in this case where you just want edges to go to 0, like you want to collapse, right? So this will correspond to harmonic mapping. Then the energy is very simple. It's sigma 1 squared plus sigma 2 squared. Right? This is saying that you don't want to stretch that out. Yeah? Or maybe as Matt suggests, what I do is I say, okay, well, what's a low distortion map? Somehow it's the one for which the condition number, like the ratio of sigma 2, which we'll assume is the bigger one, doesn't matter, to sigma 1. Maybe that should be 1, right? So maybe what I do is that. Yeah? So I say, well, I want this number to be close to 1. So I'm going to subtract 1 and then square, so now that's a reasonable objective function. Actually, since you brought this one up, this one has a really interesting property, which is not 100% obvious from if you're not used to looking at this kind of thing. So it only depends, obviously, the way I write it here, on the ratio of sigma 2 to sigma 1. So this is actually what we would call an area scaling invariant, right? So in fact, if I could have a really bizarre map of a triangulated surface that takes some triangles to be like 50 times as big and other ones to be 50 times as small, and as long as the angles are preserved, I'm actually happy because all this thing depends on is the ratios of the signal values. Yeah? So okay, so this thing is the harmonic mapping one. We're not convinced that that always works because it just wants everything you can track to a point, right? There's another objective which is very, very popular in the computer graphics literature, which is called as rigid as possible, right? This thing is equal to sigma 1 minus 1 squared plus sigma 2 minus 1. So do you guys see what this objective is doing? What it's saying is that I want this diagonal matrix to be roughly the identity. Yeah? So in other words, I just want my motion not to collapse to a point, but to be a rigid motion. Yeah? So this makes a lot of sense. Yeah? There's one detail which gets in the way of as rigid as possible. Let's say that I'm doing just planar mapping, which is that U and V in the singular value decomposition, they don't have to have positive determinant. They can flip triangles upside down. And for certain applications, that's really not desirable, right? So maybe I'm deforming a shape and I don't want to change orientation, right? The as rigid as possible energy actually doesn't really care about that. So one small modification of this thing that people use, something called the symmetric Dirichlet. Oops, that should be capital D. Which, if I remember, says, I'm sorry. So this is the Dirichlet energy that we talked about before. But then we also just add. Right, so this is sort of like adding a barrier function that prevents stuff from flipping over. Right? It's easy to check that this thing is minimized for identity matrices. So anyway, essentially when you're reading mapping and parameterization papers, before people kind of realize that this abstract kind of framework fits a lot of these different methods, essentially lots of people were proposing different functions with singular values and then optimizing. So it's easy to follow this kind of work. Right? And if you write it in this way, it's immediately clear what your algorithm is trying to do. Right? The Dirichlet energy wants everything to collapse to a point because it wants all your singular values to be 0. The as rigid as possible energy somehow wants identity matrices. This weird thing that Matt proposed wants a conformal map, and so on. Yeah? So hopefully you get the name of the game here. And in fact, in the slides for fun, I sent a pointer to a recent paper that essentially just says, okay, so many people have proposed different ones. Let's just make a giant table of all of them. And then this paper is on optimization techniques that say, okay, I don't care what this function f is, I just want to optimize it. And so what we're going to do is test on all, I guess in this case, 6 different ones and just show that our algorithm is pretty effective for all. Yeah. There's a different way to go. An open challenge here. This appears in a paper on surface parameterization, right? So in other words, taking a 3D surface and mapping it into the plane. If you'd like to optimize directly for the map from one surface into another by minimizing one of these objectives, as far as I know, this is a 100% open problem. We don't know how to do it. We can approximate it, and lots of algorithms essentially you can view as approximations of this, but even showing that they reach a local optimum is quite challenging. And part of that is sort of structural, right? That you have to decide what it means to measure the Jacobian of a map from one triangulated surface into another. It's not totally clear. So there's a lot of questions happening. Okay. So this concludes part one of our discussion of correspondence techniques. And this is, in a sense, the most obvious thing to do, right? This is what we call a variational approach. Right? I write down some energy which measures how good my map is, and then I say I want to minimize it, I close my eyes, I pray, I put it into my optimization tool, and I hope something good comes out. But the problem is that, essentially, these methods, notice, are convex only when this function f is convex. Fun fact. And so in particular, actually that's not even true. When it's a function of the eigenvalues, right, rather than the singular values. Anyway, the convexity of these things when you start engineering functions f is really hard to think about. And for most interesting mapping objectives, including as rigid as possible, including mass-varied energy, which I'm sure has a name, including the symmetric Dirichlet energy, all of these things we don't know how to optimize other than just kind of gradient descent, right? There's very little to say about it. The only one we know how to optimize is the Dirichlet energy, and unfortunately that doesn't always work. So a different idea is to say, okay, let's challenge one of the assumptions that we set out with, right? That originally I said, okay, we're going to measure the distortion of our map by just looking at the distortion of the individual triangles. And indeed, it is true that a map is isometric if and only if all the individual pieces are isometric. But for a purpose of engineering, it may be better to understand not just these very small distance interactions between points, like the distortion of individual triangles, but also long distance ones, right? Like the geodesic distance from here to here is conserved, right? Because notice that that's kind of implicit in all this stuff, but it's hiding under a big layer of Jacobians, right? And in fact, by including some long distance interactions between points, you can kind of regularize some of the little errors that stack up by minimizing little mini distortions of individual triangles. So we actually talked about this a little bit a few lectures ago. It's too bad we're missing Kelsey and Raphael today, because essentially their project is all about approximating this Gromov-Hausdorff distance. You guys remember this? We talked about this in terms of measuring distortion of one, sort of putting a metric on this space of metrics. This is a heavy-duty thing to think of, right? So the idea is I have two geometric objects, and I want to know how similar they are. Right? So what I do is I say, over all possible mappings phi from one space into another, I can measure the distortion of phi by just looking at the maximally distorted pair of points. Right? Like if x goes to y and x prime goes to y prime, then I want the geodesic distance to be conserved. Right? And somehow there's two sources of error. One is that the map phi is just no good. Right? Like if I have a bad mapping, the distances are distorted. But the other source of error is actually geometric, right? There are certain pairs of surfaces for which there just doesn't exist a map that takes distances to distances, right? And so the Gromov-Hausdorff distance essentially is trying to measure that second thing, right? So it says over all possible maps, the maximum distortion of any map is the Gromov-Hausdorff distance, right? But notice, hiding inside of here is a technique for computing a map, right? That this outer optimization problem is some minimization over phi, and you can say the phi that realizes the Gromov-Hausdorff distance is somehow the best mapping, right? This is a little bit dangerous, right? Because this objective function only cares about the one worst pair of points, but it is one approach here, and it's actually quite similar to, in a sense, this multidimensional scaling algorithm that we talked about many weeks ago. Remember, this is for like I have some high-dimensional data set and I want to visualize it on the plane, and so I'm going to embed it by kind of minimizing the distortion of the geodesic distance between every pair of points. Right? In that case, it was just the Euclidean distance. So there's an algorithm that's very, very, very well known. This is called the generalized multidimensional scaling, generalized MDS, GMD, this technique, which was one of the very first mapping algorithms. And essentially what it said is, okay, I'm going to keep the kind of multidimensional scaling objective function, but use it on geodesic distances rather than Euclidean distances. Right? So for instance, for these hands here, you can see they show the shortest path is the path along the hand. As an optimization problem, this is really horrendous. Right? Because essentially you're optimizing over all permutations of points from one set onto another, and which is NP hard usually. And on top of that, your distance function requires computing geodesic distances, which we know is not NP hard, but also just kind of expensive, right? This is a really hard problem to do. So GMDS is a great example where, in these algorithms, essentially we only have a local measure of distortion. In GMDS, we have a global one, where we look at every possible pair of points on the surfaces, and ask that every single pair, their distances conserve as much as possible. Yeah? And this is a nice example of a problem that we like to call quadratic assignment. Unfortunately, quadratic assignment is NP hard, right? So essentially, quadratic assignment problem says I'd like to optimize over all possible permutations of points something that minimizes a quadratic function of that permutation matrix. And it turns out this is NP hard anytime that quadratic function is incommon, anytime it has negative eigenvalues. Yeah? So for example, we're going to come back to a concrete example of why quadratic matching should apply. Remember when we talked about optimal transport, I think 2 weeks ago? Optimal transport is an example of linear assignment. This is identical to this problem, except the objective is linear, and then you can actually solve a linear program. So it's this one very small change to your problem makes it completely intractable and very difficult to solve. Now, a theme in some recent research, actually mine included, is that somehow these geometry problems, the geometry of the shape is not conspiring against you. Right? Like typically when you look at the proof of NP hardness for things like quadratic assignment, like the kind of counterexamples they have to construct are pretty messy, right? I mean, you're trying to map between really symmetric, bizarre configurations of objects, and that's where you can get into trouble, right? What's actually a really interesting research problem to me is quantifying how difficult a given instance of an NP hard problem is. So somehow mapping brains is a much easier problem than mapping like knotted up weird topological objects, right? But in this abstraction that I've given you here, those are identical, right? And so in fact what we found in our experience is that sometimes really stupid numerical methods that amount to very little more than gradient descent actually are quite effective on these kinds of problems, which is exciting and surprising and also a little bit frightening because like we're clearly not setting out to solve P equals NP, right? So there's some interface in between these two extremes that we haven't quite understood very well. So the reason why this is hard from kind of a heuristic perspective is that unlike the linear assignment problem, somehow there are lots of potential for multiple local optima in this problem. Right? So the typical example here would be like, let's say that I'm mapping, and I have, I have Jared and myself, and we're trying to compute a map that preserves distances. Right? Well, okay, so I can think of two maps that will approximately conserve. He's a much more svelte guy than I am, but that approximately conserve distances. One of which would take my left hand to his left hand, and the other would take my left hand to his right hand. Right? From an intrinsic, like a distance perspective, those are the same, right? They both conserve distances, even though I've kind of flipped myself inside out in the process. And that's really what gets in the way of these quadratic assignment problems, is that you can have this potential for symmetry, and then if you take those two maps and you try to kind of average them, right, that's what convexity wants, then what's in between is no good. Right? And that's what makes these problems. Okay. But anyway, to step back a little bit, the trade-off we have for this generalized multi-dimensional scaling GMDS algorithm, one is that sort of the theory is very nice. I mean, the G in GMDS is, that's all. The G in Gromov-Hausdorff distance. These are, Gromov and Hausdorff are famous mathematicians. This is a very well understood kind of mathematical object. The problem is that your search space, like the set of all permutations of one object onto another, is huge. And actually optimizing in that space is nearly impossible to do with any confidence. Okay, so my enthusiasm aside, is there any questions before we talk about some heuristics for how to optimize this? You guys get the basic idea here of what Gromov-Hausdorff is trying to measure and how to, if you had all the time in the world, how you might compute one of these maps? Cool. So unfortunately, this is one of these areas where theory and practice really don't align very well. So in practice, there's all kinds of different tricks that you have to do to make this work and have at least some local optimality kind of understanding, right? So here are a couple of heuristics that people use to optimize this in practice. Incidentally, most of the authors in this world you'll see the name Bronstein quite a bit. These show up a lot in geometry processing world more generally, but they're the people that introduce the GMDS kind of framework to begin with. And so if you're looking for papers on this particular topic, essentially I would start on their webpage and go from there. When I say them, by the way, it's, I don't know if you guys know, I think I mentioned this before in this class, the Bronsteins are these two identical twins that work on 3D surface mapping, and the original application they had in mind was face recognition, and of course, that's, you know, they're a great counterexample to, like, you could have the best quadratic assignment algorithm in the world, and it won't be able to you know, use the 3D shape of your face probably to, anyway. But they trust each other, so I guess it's okay. They can share the same pattern. Anyway, sorry, so there are a lot of different heuristics for kind of exploring the space of permutations of one surface into another. And essentially, algorithms for GMDS and kind of related techniques typically kind of are just feeling around in that space to find something interesting, and then maybe locally tune it to get at least a local optimum for this objective. Right? You can tell by the language that I'm using that we've stepped out of math and into kind of engineering. Yeah. And so some examples here. One would be kind of course-defined optimization. So maybe what I do, so in this case what they've done is they've taken these 3D models and divided them into Voronoi cells. Remember what this means? You choose individual points and you assign them points along the surface to the closest guy, you know, and that defines a region on the surface. They tend to be kind of polygonal shaped too. And maybe, you know, I only have 100 Voronoi cells, so I can afford to spend quite some time exploring the permutations of these 100 objects onto each other, and then do some other thing for mapping their insides, right? And then do some fine tuning. Rather than, you know, these meshes typically have thousands and thousands of points, and maybe that's too expensive. Notice that 100 factorial, the last I checked, is already a very large number. So if you, even methods like this, you have to really aggressively prune stuff out in order to get reasonable mappings. Right? And so maybe what you would do is couple your GMDS algorithm with something like the heat kernel signature to at least kind of cull out matches that you know are bad. And of course, this is starting to sound very heuristic, but it's actually kind of reasonable to do that, because remember that GMDS is looking for isometric maps, it's looking to preserve distances, and that's what all these kernel signatures are trying to do too. So somehow at least they're all supporting the same goal, even if they're doing it slightly different ways. Right, so two related methods might be either you solve this problem at a coarse scale and then you go back to this co-parameterization method to kind of interpolate to the inside, or you know, a different one would be some kind of coarse-defined refinement procedure. Another issue that shows up in practice for generalized multidimensional scaling, which makes it even harder to think about, and maybe closer, I would argue, to these non-rigid ICP methods than it is to mapping, although it typically lies in that literature, is dealing with partiality. Right? So here, maybe what they want to realize is that the top half of this guy matches the top half of this centaur model. Why you would want to do this particular experiment, I'm not sure, but you could imagine contexts where it's more useful. And essentially, now your problem is even harder, right? Not only do you have to minimize distortion and figure out a permutation of one object onto another, you also have to identify which pieces they have in common. Right? And so this algorithm looks a lot like that non-rigid ICP algorithm we talked about last time, right? Essentially, they alternate between turning on and off pieces of your surface and then kind of mapping one onto the other. So returning to our kind of list of different properties we might want a mapping technique to have, well, let's take a look, right? So it is automatic, right? I mean, at least if you incorporate some of these heuristics, you can essentially give it two surfaces and it'll extract some notion of a mapping. But these algorithms are certainly not fast, right? They require querying geodesic distances a bunch of times. We haven't really argued that your maps are bijective in any sense. But they are somehow low distortion, right? I mean, their job in life is to minimize this one particular metric distortion. Unless you get a bad local optimum. Then you might get a high low distortion map, but any small perturbation of that map makes it worse, so you give up, right? That somehow your initial guess was bad, you just never got to the correspondence that you want. So I can't help but give a little tangent at this point to highlight some of the stuff that I've worked on, because it is actually quite relevant to this. So remember that if you look at the objective function for a Grove-Hausdorff distance, that one of the things that's quite expensive here is the fact that you only choose the single x and x prime pair that is the most distorted. Right? So you could imagine that, like, maybe I choose a map where the average distortion is very low, but pairwise everything looks kind of terrible. Right, so you take kind of pairs of points and you just perturb them, and as long as the maximum distortion is low, this objective function is happy. Right? And so you can hide a lot of stuff in that regime where, okay, maybe you have one pair of distorted points just because they're two different surfaces and you're going to have some distortion, and then just locally, to be evil, you kind of shoot stuff and just wiggle it around a little bit. And somehow, because of that, you expect problems like this to have lots and lots of maxima that are equally good. And so, one thing you might do, at least I might do, in fact I did, would be to say, rather than taking the maximum distortion, maybe I just look at the average. Right? I just say, I'm going to leave this whole objective function the same, but instead of this inner supremum, we're just going to add them up and divide by n. Right? And that has a different name, which might look familiar to you guys, given our lecture on optimal transport. It's called the Gromov-Wasserstein distance. Right? So here, the only difference between what we have before and what we have now is that, notice this double integral. If you don't like the integral, you can think of it like a sum. It's just saying, I look at the, okay, so I'm going to take x and x prime and y prime. It's hard to think about. Okay, so these are 2 points on these two different metric spaces. And if they get mapped together, then this distance, this difference should be small. You see that? So what do? Over all possible x and x prime, and over all possible y and y prime, I'm going to take that difference and square it. Yeah? And then I'm going to multiply it by the product of does x go to y and does x prime go to y prime. Right? So if both of those are big, right? In other words, if these two things are mapped to each other, then this number should be small. Does the objective function make sense? Notice this is exactly the same as Gromov-Hausdorff. All I did was replace max with an average. Yeah? So why is this problem a lot harder than optimal transport? It's actually kind of subtle, right? Because it looks very similar, right? We have an objective here that can look like double integral. At the end of the day, our unknown is this permutation matrix gamma, which we were able to deal with in that lecture a couple weeks ago. The only difference is that we have a product of two gammas on the right-hand side. Yeah? And that's what makes this whole problem really, really difficult. But if we forget about that for a minute, we can actually apply an algorithm that we derived a couple weeks ago to this problem to great effect. So in this case, one thing we're going to do is relax from gamma being a permutation to gamma being a positive matrix whose rows and columns sum to 1. Anybody know what that set of matrices is called? Bistochastic, doubly stochastic. And remember what we did last time when the optimal transport problem was hard? That was like the left-hand side of this thing. We added a term to regularize it. This was the entropy of the map. Right, so as we increased the entropy, we got a fuzzier and fuzzier correspondence, but we figured out that it was much easier to compute. In that case, it has something to do with the heat kernel, the domain that was sitting on top of. Well, one thing we might do, essentially, if you have a hammer, you might as well hit as many nails as you can. Right? We have this other problem which somehow resembles optimal transport, minus this one pesky t gamma sitting on the right-hand side. Maybe I throw entropy at that and just see what happens. Yeah? And it turns out this is at least a very elegant algorithm that we can't prove anything about because it's an NP-hard problem, but it's very easy to derive. Right? So the basic trick here is kind of simple and maybe not more motivating a little bit. Just to show you that this paper appeared a year ago and it's a really simple technique. So if you guys are looking for research problems, this is a wide open area to work on. Right? So essentially, right, so here are our two domains. Let's see, we have x prime and y prime, x and y, right? Remember that our unknown in these transport problems are transportation matrices, and they have 3 properties, right? With the greater than or equal to 0, the rows sum just to 1. In this case, it's like saying every point has a target, and that every point has a source. Yeah? So the only thing that we're missing is the objective function. Yeah? And so what could we do? Well, let's say that and we're going to do this in completely discrete language. Yeah? So here, let's say that this guy has a pairwise distance matrix D, and this guy has this matrix D prime. I have no idea if this agrees with the notation of the paper. I don't think it does, but that's okay. And then what do I want to do? I want to sum over I, J, I don't know why I'm doing 2 sums with 4 indices, but whatever. I want to sum over I, J, K, and L. Yeah? And let's say that I have distance from I to J, distance from K to L, right? So in other words, I have dij minus dkl squared. So this number should be small if I gets mapped to K and J gets mapped to L. Yeah? So one way of viewing that, remember that this matrix is like 1 if things are mapped and 0 if it's not, is to say, okay, I'm going to multiply that by T, ik times T, J, L. Did I do that right? Yeah. So this is going to be our objective function, subject to these constraints. Cool? And this is the Gromov-Wasserstein problem in discrete language. Yeah? And there are a lot of different ways to write this problem down. Do you see that? In particular, this is a kind of a homogeneous quadratic function. Right? Every term here is quadratic. So one way you can view this, abstractly, is that this is equal to the inner product between t and, well, some function of t. I don't even care what it is. Right? So this is some linear function of t that involves these square numbers. Do you agree with me here? Because this is a homogeneous thing. Yeah, it's a very fancy way of writing it down. Okay. So, can anybody think of a really stupid way to optimize this problem? Well, essentially, this problem looks super close to what we already know how to solve. Right? If this term weren't here, it would be an optimal transport problem. So what I'm going to do is just ignore this term. I'm going to pretend like it's a constant, and then I'm going to iterate. Yeah? So in particular, what I'm going to say is that t I'm going to solve for, I'm going to have an iterative algorithm, and in every iteration of algorithm, I'm going to have a kind of an inner problem that is also a minimization, but it's somewhat easier to solve. Right? So in particular, it's going to be t So do you see what I did here? That essentially I'm going to take the previous iterate and treat it like a constant in the next one. And I'm going to iterate. Now notice, if this thing is a fixed point, then I've certainly solved my problem, right? Because then it's a minimum with respect to A. A more tricky question is whether this should converge. It turns out the answer is actually yes. But you have to essentially, this is true for a lot of these what we call proximal minimum. You have to add a term that kind of holds you back. So I'm going to say, don't go too far away from my previous estimate, but also approximate the next guy, right? And it turns out, as long as this epsilon is sufficiently large, this thing will converge to a local optimum of this problem. Yeah. So this actually isn't our work. If you add this quadratic term, then it ends up looking like, what is it called? The Hilbert-Schmidt independence criterion, which appeared a long time ago in machine learning. So what our algorithm does is essentially just build in, instead of something like this, we build in an entropy term because we know how to optimize that in transport. And what comes out is this very simple algorithm I have on the right-hand side here. Right? So you can kind of eyeball this even if you haven't gone through every step of the algorithm by hand and see what's happening here. Remember we derived this Sinkhorn algorithm last time when we talked about optimal transport? This is for entropy regularized transport. It's just 3 lines of code that gets you there. So now that is kind of like the inner loop, right? That's like this problem here because now it says linear assignment. And then the outer loop, all it does is just replace t with lambda of t and iterate. Or rather, replace your cost matrix with lambda of t. Right? So the outer loop here is some fancy function here, right? This corresponds to that function lambda. And then I just call all my code again, and then I iterate until convergence. And we actually couldn't find a case where this didn't converge, even though we're only able to prove it for kind of sufficiently large, foot dragging terms here. So anyway, we cannot prove anything about algorithms like this, right? If we could, then P would equal NP. But at the very least, we have an efficient technique that's very easy to code and can solve some class of quadratic assignment problems. On the opposite extreme are methods that do convex relaxation. So remember, in our last class, we talked quite a bit about synchronization problems, and we argued that those are very intractable, that we have problems whose variables are on the unit circle, on the unit sphere, but we can relax to something convex, solve that, and hope that it does better. Right, so we can do a similar thing here for quadratic assignment, but it turns out the only known relaxation of this problem, that at least known by me, essentially has one variable. So like what makes this problem hard is this term here, right? And what they do is they introduce one variable per term in this sum. So if I have n points per triangle mesh, then this matrix scales like n squared. And now the semi-definite matrix that I need to kind of follow the pattern that we developed in our last lecture, we're going to have n to the 4th elements in it. Right? And so if you take a look closely at this paper, you'll see the types of examples they're able to run on have about 6 points on them, right? Because we all know this is intractable. But it's nice to know that, at least for sufficiently small problems, there are certain convex relaxations with quadratic assignment that seem to have exact recovery. That in other words, give you the global optimal solution to this problem. And that somehow kind of confirms the suspicion that we have that I talked about before, right? That this problem is maybe easier than we think it is, right? Yeah, quadratic assignment in full generality can be hard, but for the typical cost functions that we care about in geometry, even convex relaxations or just like simple kind of gradient descent looking iterative techniques seem to work just as well. Yeah? And so that's really the theme here. And so, in general, what we have so far is this continuum between, the more assumptions you put on your map, maybe the easier it is to compute, but the more assumptions you have on your pair of surfaces. Yeah. So, like for example, GMDS is super, super generic, right? It works for any metric space, whereas these triangle distortion measures, at least assuming you have a triangle mesh. So you might ask the question, which is like, on the opposite extreme, like if I put super, super strong assumptions on how difficult my mapping problem is, can I do well without all of this computational hardness? Right? That's essentially, you can think of that like the theme today, right? That somehow there's a trade-off between computational work and the challenge in your mapping problem, right? So, what is the strongest possible assumption you might put on a pair of surfaces or metric spaces? Could be that they're isometric, right? In other words, that the distance function in the map that takes you from one to the other has no error at all, right? In terms of geodesic distance. Yeah? So remember that, what does that mean? In particular, what gets conserved when you have two isometric surfaces? There's a particular operator, which is the Laplacian operator, right? Which, notice that the Laplacian operator has nothing to do with the map, right? Like I can compute the Laplacian of these two elephants independently and do calculations on those, and then try to match whatever comes out of those calculations, and that's a perfectly legitimate pipeline, right? And so if you'll recall, when we talked about Laplacian, we talked about this heat kernel map, which is this particular signature that says kind of how much heat diffuses from one point to all the other ones in a fixed amount of time, as a function of time. It turns out that the theorem you need is you only have to match one point for that map to be completely distinguishable. In other words, what you'll do is you'll instead of having this be your piece of geometry, you'll think of the geometry now as being the descriptor given to every point on the surface. And in that space, what you can prove is that they rigidly align. So what you can do is lift to heat kernel space after having one point match from one surface to another, and then use things like ICP that we've already talked about, because we know that these kind of weirdly abstract pieces of geometry, which correspond to your descriptor for every point on the surface, right? Is the lifting into R to the high n. That thing is a rigid map, even if this, like from the elephant to the elephant with his leg up, is not rigid, right? Obviously, there's bending and stretching on there. Cool? So this is an example of the opposite extreme. Yeah?
What do you mean when you say match one point? Does that mean you're trying to only solve for one?
Oh, that's a good question.
The user has to give you 1 point.
Yeah, so typically the user marks one pair of points that matches, and then you use that to construct the descriptor function. So the descriptor function is how much heat diffuses from that point to all the other ones, and as a function of time. That's a good question. Any other questions? Yeah, so this is good for Brownian motion. However, what do you think happens if I take this elephant and I just do something goofy, like I remove one of his tusks? Like I just do a very small, what somehow is geometrically a small edit. Unfortunately, that can completely change the heat kernel structure of your surface, right? Because diffusion is very non-local, right? If you ever take a PDE class, the very first theorem you'll prove about the heat kernel is that for any time greater than 0, heat has diffused your entire domain. Somehow, relativity and heat diffusion don't talk to each other very well, right? You have communication faster than the speed of light. It's like this much heat. That aside, what that means here is that the second that you break this isometry assumption, you really can't use this tool. And it's not even like one of these things where if they're kind of isometric, then this tool kind of works. There's no theorem to that regard, right? The second that there's no isometry, you really know if it's in trouble. Okay, so So the trade-off here is that now, remember the search space for GMDS is huge, right? It's over all possible permutations of one object into another. And that's a really big object, right? That's like combinatorially huge. It expands like factorial, right? On the flip side here, all I have to do is compute closest points. This is completely computationally tractable. And there's some notion of extending this to partial matching that people have considered, at least when the parts that you're chopping off are isometric. But it's extremely sensitive to deviation from isometry. So here, if you take a look at this figure on the right-hand side, what Ova has done is colored the mesh on the right, and then shown like where that color gets mapped on the other guy if you use the heat chrono map. And you can see, based on the splotchiness of these guys, that this is not a great tool to use, right? That somehow you end up with discontinuities, all kinds of stuff. That's bad, bad practice. Whereas, if you minimize the distortion measure, you would at least be unlikely to give this particular type of error, right? Because this kind of discontinuity is happening because you're just choosing your closest descriptor, so there's no notion of like nearby points go to nearby points, whereas things like GMDS are really trying to optimize that directly. Yeah? Okay. So if we return to our little continuum here, where we have super weak assumptions like I just want a map that's low distortion. I have super strong assumptions like I know there's an isometry and I'm just trying to find it. The question is, what's in between? You guys have any ideas? What's in between isometry and just kind of low distortion? Like what assumption could I put on that? It's a little more flexible. Well, conveniently, there are a few sitting on the board right here. Right? Remember that we talked about different types of functions f we could construct here, right? And essentially isometry says what? It says that you could preserve areas and angles. But you could also ask, well, what if I only asked to conserve one of those two things? Yeah? And in fact, that leads to a lot of these mapping techniques, where essentially what you're going to do is say, okay, I can't expect to find just an isometry, because typically those don't even exist. But, for example, the space of conformal mapping, the space of things that preserve angles, is quite large. And so maybe I'll search in that for a reasonable map. And at least I know that angles are preserved exactly. And maybe what I do is say, find the map that preserves area the most and preserves angles exactly. Would be one example of this process. Right? In other words, somehow isometries are hard to work with, but things like conformal maps are easier to think about. Yeah? In fact, conformal maps span a large space, right? So even if I wanted to solve the isometric mapping problem, how could I do it? Well, there's kind of an interesting algorithm here, which is say, okay, well if I want to find an isometric map, maybe I don't know how to do it exactly, that's kind of a tricky problem, I still have to minimize distortion. But one thing I can do, it'll turn out, is compute conformal maps pretty easily, given a few points that are marked. But it's only a few, it turns out 3 is enough. So what do? I say over all possible triplets of 3 points, I'm going to compute the corresponding conformal map from one surface into the other that conserves those 3 points. And then what do I know? If I iterate over all possible triplets of 3 points, and if I know there exists an isometry, somewhere in those triplets I'll find it. Right? So in other words, I have this kind of interesting technique where essentially what you can do, an algorithm for extracting a perfect isometry from one surface into another, says I'm going to iterate over all possible conformal maps and just find the one that's isometric, because I know it's hiding in there somewhere. And so I don't think we have time to talk about it today, so maybe we'll stop a couple minutes early. But essentially, we're going to talk about an algorithm called Mobius voting. The idea here is that you first work really, really hard to come up with a smart algorithm for taking a surface and conformally mapping it into the plane. Incidentally, is it clear that we can do that? No, the way that I described it, right? Because like the plane does not have the same topology as the surface, right? But there's one way to fix that, which is to consider what we call the projective plane. Right? So you take the plane and you add points at infinity. I don't know if you guys have seen this construction before. Right? Certainly if you take a computer graphics class, you have. And essentially, we will conformally map a surface into the projective plane. And then you can parameterize the self-maps of the projective plane very easily. These are called Mobius transformations. There's this little slick video here. Maybe we'll actually watch it eventually, but you can see there's all kinds of cool conformal maps of the plane. That you can see that all the right angles here are conserved, even though they're bent in all kinds of funny ways. And they can all be parameterized using just complex value functions that look like this thing on the right-hand side here. These are called Mobius transformations. Right? So at the end of the day, all you have to do is find A, B, C, and D, and you have yourself a conformal map from one surface into the other by conformally mapping into the plane, conformally mapping the plane into itself, and then conformal mapping to the surface. And so it's conformal maps preserve angles, and that's the kind of property that's conserved under composition. Life is good. Yeah, so that's going to be the kind of the high level outline. So anyway, over the next couple days, I'll let you guys think about that. On Thursday, we'll fill in some details of this method, and then this will suggest what I think is kind of state of the art for just generic mapping techniques, which is this blended intrinsic mass paper from a couple of years ago. So with that, we'll stop. A reminder that you should be like working on your projects if you haven't been already. If you're stuck anywhere, please contact me. I don't want to see lame projects because you woke up in the middle of the night the day before it was due and realized you couldn't code something you thought you could. Right? So if you know that you're susceptible to that, or if you're already feeling a little stuck, email me and we will find a time. I can't say that enough. Your professor has no life. He's willing to put extra time into helping you get a better grade. Cool? Alright, that's our agreement. Alright, so we'll see you guys next time. Somebody can hit the button on the camera. We much appreciate it. Alright, we'll see you then. You can come together anything you like. You done with your project? Wow. Okay.
Well.